Happy hump day. It's Wednesday, and I hope you're missing me. I'm surely missing you. Of course, it is Friday when I'm making this recording, but I know I'll be missing you by Wednesday. By Wednesday, I'll be wishing they gave me the last 2 days off. Sometimes they did that last in prior years. Like if we were ahead or we didn't need all the people at a testing site, they'd say, oh, you can go home. In the last 2 years, I was home 2 days early because I have to be out again for Keystone testing in May, but anyway, I'm told that's not going to happen this year. So I'll be wishing I was home to teach you guys. In any case, welcome to Wednesday. Today we are chugging right along, working on lesson 12 in states of matter. So that is, again, just to be totally clear, that's lesson 1.12. Okay. In this lesson, we're talking about a different scientist and another gas law. But this is by far, I think, the most straightforward, and that is the Dalton's law of partial pressures. Now, before we get started actually talking about partial pressures, as is typical, I try to relate this to what you can understand or know or think of in your world and how it's similar. You might be thinking to yourself, how is whatever that is similar? Maybe, hopefully, you've seen A Christmas Story. Have you seen A Christmas Story? This is going to be a survey question. I'm going to ask you to actually put that in there because I run into classes where actually there's a ton of people who haven't. It's a very classic Christmas movie, and while I realize everyone doesn't celebrate Christmas, it does run 24 hours on TBS on Christmas Eve every year. So, have you ever seen A Christmas Story? Okay, well, in this movie, there's a little boy named Randy, and his mom dresses him up and bundles him up so much when he's going out to play in the snow. You can see he's got, you know, his hat and his scarf and probably a sweater and all kinds of snow stuff on. He can't even put his arms down, poor kid, right? So let's play with this a little bit. And I say, well, if Randy weighs about, well, I don't know, 60 pounds, he's probably 8-ish. He weighs 60 pounds and his clothes weigh 20. Then how much is the entirety of Randy going to weigh with his clothes on? 80, right? Let's mark that down. He's going to weigh 80 pounds. Why? Because Randy weighs 60. And we add to it his clothes. So this is a little bit of a simple addition problem, right? 80 pounds. If we take his clothes off when he comes, his snow clothes, that is, off when he comes in from outside, let's say he didn't even get to playing in the snow because he watched his brother get beat up in some part of this movie and he ran home. We take off his snow clothes, let's assume they're not wet, nothing happened to them, and we put them in a pile. Does the weight of his clothes in the pile or the weight of Randy change just because they were separated? Answer yes or no. No, absolutely not, right? No. They don't change. We didn't do anything to them to change. Conservation of mass, right? It can't be created or destroyed. This is a mass example. We're not dealing with masses today. We're dealing with pressures. But the same is going to be true. What we're going to talk about today is the fact that pressures of different gases are additive. So to relay this analogy back to chemistry, we're looking at a scenario where we have two gases, some gas 1 and some gas 2. And gas 1 starts out, you can see here, with a 50 Pascal pressure. And gas 2 starts out with 100 Pascal pressure. And then we say, well, let's make a prediction. We're going to open these valves and have them mix in the center container. What do you think the total pressure will be from gas 1 and gas 2? It'll be 150, right? 50 from gas 1 plus 100 from gas 2 is going to equal 150 just pascals, not kilopascals. Just pascals from both gases. If you predicted that, way to go. That's where we're headed in this lesson today. So we'll spend some time clarifying that. If you don't quite understand it, I promise it will get clearer. Today, our two goals are to use Dalton's law. First, learn Dalton's law, of course. Dalton's law has to do with not just the pressure of a gas, but the pressure of multiple gases, as you'll see below. Some pressure of gas 1 and pressure of gas 2, and whatever else there is, being a sum. a simple addition solution to these problems. So we're going to use Dalton's law to determine total pressure, just like we did in that last example. And then we're also going to define and calculate partial pressures using this law. We're going to start with another real life extension, or what is this about? Why do I have to learn this, Mrs. Carosa? It's chemistry and pressure. Isn't that a physics thing? It is, but you know what? It's also an environmental thing. So when we look at the gases in our atmosphere, we look at the fact that most of it is made of nitrogen, right? 78% of our atmosphere, the gas we're breathing, is nitrogen. Our lungs know how to filter out the nitrogen, and we just breathe in the oxygen. The oxygen is only 21% of that gas sample that we're breathing in. And then there are some other gases. We have a very small percentage of argon and a very small percentage of CO2 floating around in the atmosphere. So the gases in our atmosphere are a mixture. And that's what we're talking about with Dalton's law. Mixtures of gases. We are never, ever, ever using Dalton's law if we have a pure gas. Pure nitrogen, no way. Pure nitrogen, we can talk about Boyle's, Charles, Gay-Lussac's ideal gas law. We're not going into Dalton. Okay, we're looking at a mixture like this. We're playing with Dalton's law. And Dalton was a scientist who specifically decided that he was going to sort out what's going on when we mix gases. And this was way back in 1801. I mean, I think they were pretty sophisticated way back then, right? All of our fundamental science came from times where we had none of this fancy instrumentation and nothing really, comparatively speaking. So it's pretty impressive that they've done what they've done. In any case, he said that there were three basic ideas that we should consider about gas mixtures, and that is that the mixtures behave the same way as pure gases. So, I mean, now this excludes biology. Of course, our body doesn't deal with nitrogen the same way it deals with oxygen. But in terms of molecule movement and you know, all the principles we've learned, volume increases when pressure decreases and volume increases when temperature increases. Those gas mixtures, like air, like we can do those experiments by blowing our own air into a balloon, because the mixture of gases from the air or from our lungs behaves the same as a pure gas as if we went to the store and got some helium in the balloon. Additionally, he said individual gases behave independently of the mixture. Think about when you meet somebody, guy or girl, and you're interested, and then you couple up. Or in marriage, right? Okay, you're two different people, you come together, you create one new life together. Hopefully, once you are coupled up, boyfriend, girlfriend, you still believe in the same things you believed in. You still like to dress the way you like to dress. You still, you know, you preserve your own morals and values. You don't automatically meld into another person. It's exactly the way gases are. They're misindependent. They like to be their own body. And so gas A that mixes with gas B is still going to behave like gas A. And that includes retaining its own pressure. So that leads to this idea that individual gases contribute to the total pressure of the mixture. And this is where we get that idea that we want to sum or make this an additive property. Okay, and all of this has implications in very practical uses. First and foremost, we like to talk about scuba diving when we talk about this lesson. I'm not going to go into great depth with it here. We had more time in prior years, but there's a whole thing about scuba diving, if any of you have ever done it. A tank of gas in scuba is not 100% oxygen, as I'm sure it's probably not if they give you oxygen at the hospital, you know, in one of those little masks, because your body doesn't know how to deal with entirely oxygen. It does actually need to filter out the nitrogen and do some stuff there. So when we're providing, you know, supplementary air in a situation of a crisis or scuba or something like that, we need to have this sorted out. Flying aircraft at high altitudes, we have to consider the changes in pressure and the air that is going to be available there. Even mountain climbing, you're changing the pressure because as you go higher in the atmosphere, the pressure decreases, becomes colder. And of course then doing chemical reactions as well. So the hypothetical situation I posed to you in the beginning of class is an interactive in the course. So on these days that I'm not there, as is every single day, you should always log into the course, read the lesson, back up what I said. Don't trust me inherently. Make sure that you are also doing your due diligence in the course. And as I always try to really like pump up these interactives and these simulations, on slide number 4, you can actually see these molecules bebopping around inside of their gas containers, and it tells you the pressure of them. So gas 1 is 50 pascals, gas 2 is 100 pascals. I'm not going to show that here today, but when you do open the pumps and you will allow those gas molecules to float in, you can see the red and the blue. They don't change color on purpose in this simulation because they behave independently of each other. One goes in red, it stays red. One goes in blue, it stays blue. Now gas molecules don't necessarily have color in real life, but this is just to demonstrate that they stay independent. They also come together to contribute to a new total pressure, and that's one of Dalton's theories or his properties of his partial pressure law as well. And they combine to create a total pressure of 150 like we looked at. Now, in a mixture of gases, we said each gas exerts its own pressure on the container. These are called partial pressures. Okay, so there's the total, this is the total pressure when we have a mixture. But individually, independently, each gas has its own partial pressure. So in any mixture of gases, those partial pressures come together and we add them to get a total pressure. Mathematically, it looks like this. In the lab, it appears this way. Mathematically, we do this, okay, where we have P total equals P1 plus P2 plus P3 and so on. So the dot, dot, dot means we can have 10 gases. We can have 20 gases. We can have 100 gases. And we would just be adding all of those pressures together to get the total pressure. Another way you may sometimes see this, and you will see this in problems written in quizzes and tests and even throughout the content of the lesson, in the course lesson, is perhaps you're dealing with oxygen, nitrogen, and hydrogen as actual gases. You might see this denoted with capital P to indicate pressure, and then subscripts with the formulas of the gases you're working with. So if you were using, for example, oxygen, nitrogen, and hydrogen, it might look something like that, and you're going to add those all together. And it's totally up to you the notation you want to use when you're showing your work, or you are doing your homework, or you are, trying to work out a problem. You can assign 1, 2, 3 to the different molecules. Just be sure to be consistent. That's how we avoid, mistakes in our math. Okay. So I'd like you to pause for just a moment. We're going to pause for a minute. And I'd like you to tell me, in this experiment where we have mixed these two gases, in this final, in this final scenario where we have a mixture of gases at 150 pascals, I would like you to tell me, what is the partial pressure of gas 1 in that mixture? That is the red gas. If you said 50, you would be correct. Why? Mrs. Carroll says, well, and I should have probably, I think I lost some graphics there when I was changing things to be able to have my video on the screen. This started at 50, right? Hopefully you remember that from the beginning of class. And the blue one started at 100. So if it started at 50, Miss Independent, she doesn't change herself, right? She goes into the mixture and she retains her 50 pascals of pressure. So 150 is going to be the total. That can't possibly be a partial pressure. Partial, of course, means part of the mixture, part of the whole. That would be the total. And then we'll get to the other one. In fact, right now, we'll say, what is the partial pressure of gas number 2 in this mixture? Same mixture, gas number 2. Okay, hopefully you said 100. Gas number 2 started with a pressure of 100, and it took with it a pressure of 100. 150 is the total pressure of the entire mixture. When we talk about partial pressures, we say these little blue guys took the same pressure with them. They're having the same number of collisions as they did before. That's its contribution. Think of partial. Partial equals a contribution from one gas to the whole. Okay? We'll try some examples. Now I have some straightforward examples of just addition and summing and solving for total. Let's solve for total pressure first in these examples. A mixture of oxygen, helium, and argon has the following partial pressures. Pressure of oxygen is 152, pressure of helium is 340, and the pressure of argon is 76. What is the total pressure of the mixture? Go ahead and log your answer. Okay, let's set this up. I'm going to be very thorough. I'm sure you guys aren't being this thorough, but I'm going to be very thorough because I'm the teacher and I have to be. We have P, whoops, again. Let's do P total. P total is going to be equal to each of the sum of all of the pressures of all of the gases in the sample. So we have partial pressure of oxygen plus the partial pressure of helium plus the partial pressure of argon. So just matching these up, our pressure of oxygen is 152, our pressure of helium is 340, and our pressure of argon is 76. I can do that in my head, but I don't want to. I get 568. And I know I didn't have to do that. I know some of you are on the other end going, Ms. Curtis, you don't actually have to do the math to answer these correctly. But you do if you didn't have multiple choice. You guys are just lucky dogs. You get some multiple choice. So if you were solving this as an open-ended problem, this is how you would solve it. And your total pressure is nothing more than the sum of the individual pressures. Now let's look at our options because I like to help you out with test-taking strategy too, of course. Pressure of oxygen is 152. That means the total pressure could not be 152. If you answered A, you excluded or didn't think about helium and argon. Similarly, the pressure of helium is 340. So the answer can't be 340. If you were looking at that, you were neglecting oxygen and argon. And same thing with 76. If you chose that, you were neglecting the other two gases. The only really reasonable answer here was B. But you need to know how to do it. So I've shown that to you there. You should do wonderfully on the next two examples. This one says a tank of gas has partial pressure of nitrogen and oxygen equal to 1.82 times 10 to the 4th kilopascals and 5.32 times 10 to the 3rd kilopascals respectively. That means nitrogen is this one and oxygen is this one. What's the total pressure of the tank? Now, you have scientific notation in here. I'm going to recommend you take it out of scientific notation to do your work and then put it back in. Log your answer, A, B, C, D. Okie dokie. If you look and see here from your choices, we have two sets of numbers, a 7.14 and a 2.35. And the only difference between your answers is the exponent. We're looking 10 to the 4 or 10 to the 7. So all four answers are very different from each other, but clearly, you know, you can kind of do a process of elimination here because your front number is either going to be 2.35 or 7.14, and your exponent's either going to be 4 or 7. You just have to know the ropes here. So adding in scientific notation is not as easy as adding normal numbers. That's why I recommend you take it out. I'm going to go ahead and write here. 1.82 times 10 to the 4 is equal to, now this goes back to when I wasn't around and I was sick those couple days and we did not really go over scientific notation, but I provided you with some videos and extra help, and I gave everyone who asked extra help on those lessons. So don't come crying to me when you don't know about this, because you should. Taking 1.82 times 10 to the 4th out of scientific notation, we would be moving this decimal place 1, 2, 3, 4 units, and then we have a decimal place. So that means we would be inserting 2 zeros. The final number here then in ordinary notation is 18200, 18,200 kilopascals. Okay. Let's convert the other one. 5.32 times 10 to the 3rd. Same methodology used here. We move the decimal place 1, 2, 3 places, and we insert 1 extra 0 at the end. So our new number is 5,320. So now hopefully here you can see why you can't just straight up add 1.82 to 5.32. Because the 5 doesn't align with the 1, it aligns with the 8. That's how you have to add it. So let me just be real clear. See, this is where we're adding these two digits. So we add this together, we get 23,520. And now we just put it back in scientific notation. So we start with our decimal place here and we count 1, 2, 3, and 4 spots. That gives us, oh, I don't even know if you can see that, huh? Let me see if I can move it. Nope. Let me do it over here. 23,520. We're going to move our decimal place 1, 2, 3, 4 spots. That equals 2.35 times 10 to the 4th. Okay. So if you knew you had to add, wonderful. But number one, know that adding scientific numbers, scientific notation numbers, you never add exponents. You never do. Never, ever, ever. So that would automatically rule out, let's see here, the 7s, the 10 to the 7. No, we wouldn't entertain those. Now, if you were adding 5.32 and 1.8, you would get 7.14. But again, we're not doing that there, right? We have to add in succession the units that go together, the ones place, tens place, the hundreds place, and so on. Okay, so now that I've given you the instruction on that, because I know that's a whole other element, it's not just simple addition, it's scientific notation addition. And again, I encourage you to use this method where you actually take it out of scientific notation, then put it back in to get the answer correct. Try your hand at this one. We have nitrogen and oxygen, two pretty large scientific notation numbers. What's the total pressure in the tank? All right, total pressure in the tank. I'm trying to find some pen colors here. Exponents of 5 and 9, and I believe I just got done saying never add exponents when you're doing addition. I'm not going to write all that here, but you do add exponents if you're multiplying these numbers, not when you're doing addition. So your exponent is not going to be 9 right away. No. You have 50-50 shot here, 2.55 or 5.38. You can note that these are two different numbers. This is going to be at 10,000s, and this is going to be almost 100,000. So let's take these out of scientific notation formally and see what they are. 2.24 times 10 to the 5. is going to be equal to, taking our decimal place and moving 1, 2, 3, 4, 5, new decimal place. We're adding in 1, 2, 3 zeros. Our new number is 224,000. 224,000, 3 zeros. And then our other number, 3.14 times 10 to the 4, is going to be equal to, moving this decimal place 1, 2, 3, 4 places, going ahead and inserting 2 zeros. New number is 31,000, wait a minute, 31,400. We add those together and get 255. I'm not sure if you could see that behind my image there. 255,400. Now, we put it back into scientific notation. 1, 2, 3, 4, 5 positions we move our decimal point. 2.55 times 10 to the 5. And that gives us answer A. So if you answered A, awesome. If you answered B, you were still trying to add these two guys, and you don't want to do that. Not when your exponents are so different. They're the same, no problem, but they're different, so you can't. Okay, that's total pressure, totally whacked out. The hardest you'll do is in exponents, but I'm sure they're on the quiz. Okay, so we have, and you can't see this, I forgot to adjust this slide. We have used Dalton's law to determine, well, maybe I can. We have just used Dalton's law to determine the total pressure of a gas mixture. Now we want to work on focusing on working with partial pressures, just calculating partial pressures. So if we go back to this equation for Dalton's law, instead of calculating this guy, we want to calculate these folks. And you're going to say, well, that's easy. Instead of adding, I'm just going to subtract. Put one equals, like one of these are going to equal X, and I'll know the rest and do some subtraction. That is one way to do this. That's one way to approach it. In fact, there are 3 ways to approach it. And that is the middle option here. Okay, Dalton's law, where we set each partial pressure equal to the total pressure, and as long as you know everything except one pressure, you can just use simple subtraction. But we can also use the ideal gas law, which is not a method we're going to do as an example today. It's a little bit more sophisticated, and it's not on quizzes or tests, so we're just going to skip it for today. We are, however, because in the real world, so many mixtures are presented as percentages that we will definitely address the situation where we have a percentage of a gas. Like we went and looked at our gas mixture in the environment earlier. We said there's 21% oxygen, 78% nitrogen. What we can do is basically say what pressure is oxygen exerting when the total pressure is 100, for example. Okay, so we're going to do a few of those examples now. And actually, we do have 3 examples. And I will show, actually I lied, I will show the ideal gas example. We're going to show 3 examples, and I'm going to show this list each time we show an example. And I'm going to ask you multiple choice, which technique would you use under each of the circumstances? Because you're going to be presented with different circumstances on your quiz and on your test. And we want to know that you know how to go about answering them, not just follow me along, right? So let's start with the first question. It says a mixture of argon, helium, and oxygen have a total pressure of 2,015 kilopascals. The partial pressure of argon and helium are 152 kilopascals and 305 kilopascals, respectively. What is the partial pressure of oxygen in this mixture? First, I want you to tell me which technique would you use to solve this? Ideal gas law, Dalton's law, or percent composition, calculating percents. All right, hopefully you picked Dalton's law, because we have a total pressure of 2,000, And then we have individual pressures of argon and helium. So let's set this up, and I'm going to be real thorough about this. Again, you may not be. We have P total equals the pressure of argon and the pressure of helium. And we know P total is 2,115. We know the pressure of argon. Oops, we have oxygen too, pressure of oxygen. So that's our unknown. This is the thing we're solving for, right? 2015, argon is 152 and helium is 305. Pressure of oxygen is just X. We don't know it, it's unknown. So solving for X, we might simplify the left-hand side first and say this is equal to 457 plus X. Solving for X algebraically, because we're doing addition on the right-hand side, we're simply subtracting 457 on the right-hand side to give us X, and then 2015 minus 457 is going to give us our pressure. 2015 minus 457 is 1558. And we want to put it back in units that were given to us in the problem. So that's kilopascals. So this is just a rhetorical question, really. I'm not going to have you answer it. No, I lied. I'm going to have you answer it. Would you say there's a lot of oxygen in this mixture according to the pressure it exerts, or just a little bit? We have a total pressure of 2,000, and you know this is additive. Do you think there's a lot of oxygen or just a little bit? There's a lot. The pressure of oxygen is hugely contributing, more than half of the total pressure in this example. So oxygen is a considerable component here. Okay. Calculating partial pressure is a different way. At a depth of 30 meters, the water pressure is 400 kilopascals. A diver breathing air that is made up of 78% nitrogen and 21% oxygen at this depth would have what partial pressure of oxygen in his lungs? Again, are we looking at the ideal gas law, using ideal? Now we've already used the Dalton's law, so I'll eliminate that for you. Are we going to use the ideal gas law to solve this, or just based on percentages? Right. If we're given percentages in the problem, it's pretty safe bet that we're going to be using it to solve the problem. Okay, the other thing here about this one is it doesn't tell us the mixture of the air is at a certain pressure. But we can assume, like if we have a little scuba tank, and I'm not a good drawer here. This is going to be like a pressure gauge. This is a scuba tank. And in here, on the outside, what it says is the water pressure is 400 kilopascals. So what has to happen in scuba, and you don't necessarily need to know this to solve the problem, that it's a scuba related thing, but the pressure going out as well, the pressure of the gas has to be at least equal to it. So we can assume that the total pressure of the gas inside is 400 kilopascals. So if our percent composition of nitrogen equals 78%, and our oxygen is 21%, and this is P total, we're going to go ahead and use this equation where the pressure of the gas equals the total pressure times the percent of that gas. Now to work with percents, we should always be converting to decimals. So to do that, we're dividing by 100, right? Moving the decimal place. So 78% ends up being 0.78, and 21% ends up being 0.21. And we're going to multiply each of those by the total pressure, which is 400. Now the question just asks what's the pressure of oxygen contributing here. But I'm going to go ahead and solve for both of them so that you can see it's done this way for each component in the mixture. 78% of 400 works out to be 312 kilopascals. And 21% of 400 is 84 kilopascals. All right. The other way you could solve for the second one, if we asked you to, is realize that 312 plus 84, wait a minute. .312 plus 84, what's that equal to? 396. That's 4 short of our total. So you might be thinking to yourself, shouldn't that equal the total? If we add them up, those are the only 2 gases it says that are in there. Perhaps, but 78 plus 21 is only 99%. So there's a 1% of some other gas there. And 1% of 400 is equal to 4. So there's 4 kilopascals we can't account for because we don't know what gas is there. Okie dokie, one last example. And in this example, I'll just share with you now that we are dealing with using the ideal gas law to solve it. So I'm going to leave you to pause the recording and play with this one if you want to. This is more practice with the ideal gas law that we have learned about. Here you know your volume is 7 liters. You know your, let's see, you know 2 different numbers of moles, and the question is asking for partial pressure of fluorine. So your N is going to be concerned only with the number of moles of fluorine gas, and here that is equal to 3 moles. Oh, we have 1 mole of hydrogen too. So just to be clear, the 3 moles of F2, let me put that in a different color so you can actually see it. The 3 moles of F2 are the only ones that we're concerned with here. Your temperature is 273. You're solving for pressure. And since you're solving for pressure, it doesn't matter which of these you use. You're going to solve for the partial pressure of fluorine. Now you can do the same process except using the number of moles of nitrogen to get the partial pressure of nitrogen. And you could use the same equation, PV equals nRT, to solve for P of hydrogen as well, if you use the number of moles of hydrogen. And again, so that's 3 different practice opportunities for you for the ideal gas law. Okay? Wrapping this up, as I said, Dalton's findings have important implications in all kinds of things that we do recreationally as well as in chemistry. One example of this is to consider the partial pressure of oxygen just in our atmosphere. Again, we talked about mountain climbing. If any of you are hiking enthusiasts or you often climb, that part of the reason climbing Mount Everest is such a challenge and such a feat for most people to overcome is because the air pressure lowers so much up high. And if the air pressure is totally lowering, then the oxygen pressure available to you is lower and you have less oxygen up there. It's difficult to breathe. When it's difficult to get oxygen to various muscles and tissues in your body, you can't move as well. You don't have as much strength. Your brain doesn't properly function. So that's part of the reason for a change in oxygen pressure as we go with altitude. And then with scuba divers, there's a whole thing with, we don't talk about it much here, and everything on this slide is really sort of not important, but or redundant, I've already said it. There's a whole thing with the type of gas that you provide, and it has to really be exactly 78 to 21% oxygen, nitrogen, or you get nitrogen bubbles in your blood, and there's like a whole thing that happens with ascension, coming back to the surface. When you dive deep down, the pressure is different than when you come up to the surface and you're in the tank, and your body has to regulate that, or you get very, very sick. You have to be in a hyperbaric chamber. It's a whole to-do. So chemistry applied to your world. Be careful when you're scuba diving and have somebody very skilled helping you. Make sure too that they know something about chemistry and the gas laws, and if they don't, you can inform them. Okay, that does it for Dalton's law of partial pressure. We're only spending a day on this, and I don't have supplemental problems for you, as is the case with most of the other gas law lessons we've done. I've left alone many of the examples in the course so that if you're needing more help, especially when I'm away, you need more walkthrough, you need to see it worked out, or you need challenged for yourself and you want to try a problem and see if you get the correct answer, go ahead and log into the course. There's plenty of examples there for you, and you can see the entire solution worked out to help you sort of work your way through yours, should you get it right or wrong, or whatever the case might be. We were on Wednesday. So, do I have that slide here? Nope, I don't. I didn't include your, let me see if I can do that here. Nope, I can't. Nope, I can't. Let me give you a new slide. And I'm just going to recap, okay, because I like to do that at the end of every lesson. Monday, you had lesson 1.10 quiz to complete. Tuesday, that was yesterday, you have lesson 1.11 quiz to complete. And on this lesson, you want to complete this quiz as well today, 1.12. And this finishes up our States of Matter unit. We are leaving gas laws in the dust. Tomorrow, which is Thursday, I will come to you with a recording summarizing this unit. It will be less interactive, maybe. I don't really know. I haven't planned it yet. Than is typical for a review. I will make a worksheet. You will get that worksheet to work along with me. So there's a review worksheet, review and worksheet, and that will be mandatory. And it will be worth a couple points in the grade book. And then Friday, there will be no video to watch. But I will send a PDF of references, or how about we use the word resources, for helping you complete this, because I want you to have certain equations and have certain gas constants and not really be, whenever we do a test, I always have you meet in the course and I summarize the test for you and all of that. So a supplementary document for that will come out, but there will be no video for Friday. One more installment this week before I see you again on Monday. Have a great one.